Oh, okay. Yeah, so let's begin with a brief introduction. So many security sensitive applications use smart cards for encryption, decryption, and digital signatures. And these cards are used in many everyday operations, such as government IDs and secure authentication systems. But however, while these like smart cards are designed for cryptographic to keep cryptographic operations secure, they may unintentionally leak information. So cryptographic algorithms such as RSA and ECDSA cause power fluctuation, and this power reveals cryptographic operation panels. And then through that, they're directly connected to the LED, which can reveal sensitive information. So let's talk about the threat models. So we have two threat models here, which is close video acquisition and over the video acquisition. So yeah, for the first one, you have to have a camera in close physical proximity and such that the LED is in the full frame of the camera. So as you can see in that diagram right there, like that's close video acquisition, where like your phone camera is right up to the power LED of the device. So we classified it to a low to moderate threat because it's really hard to get like the camera to go right up to that LED. And then we have another threat model, which is over the internet video acquisition, which requires like a compromised camera, such as like, your computer webcam. That's also a very low threat because it's very hard to position the camera such that it's in full frame of the LED. And you don't really know when you're going to do that. And then another caveat to both of these is that the device has to be actively performing cryptographic operations. So like before, when we were talking about like card keys, like it has to be performing those cryptographic operations when you're recording. And then we classify this as a power and optical side channel. Power because we're trying to measure the power of the system or the target. And then yeah.
Okay, so to give more background on our system, so most cameras use a process called rolling shutter to take videos and image frames. So if you think of like a video as like a sequence of image, each frame of the image actually doesn't happen in the singular instance of time. And that's the process of rolling shutter. So if you look at the diagram on the right, you can see like there's a little bit of distortion for the image because the top part of the frame actually happens in time before the bottom part. And what you expect is that you would have a camera have global shutter, which is the illustration on the right, but many systems, even like a lot of high quality cameras use rolling shutter. And on this image on the left, you can see like directly that each frame happens like the row before actually happens after in time. And so there's gonna be brightness variations per row, and those will correspond to the LED power fluctuations. And each frame will actually have a different brightness encoding for each row. So if you think about images of different rows, each row will have a different brightness level.
Just stop working.
Frozen?
Yeah, it really just doesn't work. Yeah, the slideshow's just like not working.
Yeah, it's like
It's literally frozen.
number of tabs.
I also on Chrome too.
No, it's not that, I swear. I don't know what it is. Let me stop showing.
It's self-inflicted.
Yeah.
Okay, so the author's process for data extraction. So normally like the camera's FPS is a lot lower than the frequency that an LED can flicker. So to actually get accurate responses that you need to upsample each frame, and each frame can give you around 60,000 samples per second. So and actually the process what they have for what John said earlier is that they have to zoom in all the way to the LED light where there's no background noise, because we only want to capture the brightness. Like the shape of the LED doesn't matter at all. You just only want the brightness levels, so you can extract that into power intensity levels. So they measure the LED brightness and they extract that into light intensity levels. And if you plot the over time, you're able to get power measurements. So if you look on the graph on the left, you can see that every couple hundred samples has a different fluctuation. And actually each fluctuation in the power can kind of represent some sort of cryptographic operation, whether it be like a 1 or 0 pattern, and then that could be traced into power. So if you see on the illustration on the right that the frequency and time kind of illustrate on like a bright pattern. So that bright pattern could reveal responses on like what type of cryptographic operations that are occurring per each instance of time.
Quick question, the device that you're looking at, the LED, what is the device? Is it like a pose?
Yeah, so normally it's like a card reader.
Card reader? Okay.
Yeah. I guess before we had an illustration of the device kind of, but
That's fine.
could you go back? Yes.
Okay, so key recovery. So now that we know that we can use the information leakage from like the LED brightness fluctuating, we can use that to calculate the signing time with an attack known as a Minerva attack. So the Minerva attack takes advantage of it's used to extract the key from an ECDSA algorithm, which is used for digital signatures and verifying the authenticity of online stuff. So how the Minerva attack works is that most algorithms, when implementing the ECDSA key encryption, they truncate their for loop based on the number of leading zeros, and that can lead to a variable time in how long it takes to run the entire algorithm. As you can see on the heat map there, based on the leading zeros, there is some kind of correlation that as the leading zeros increases, the time for the entire operation slightly decreases. So you can use that to extract the nonce of an ECDSA key. Why extracting the nonce is important is because in an ECDSA key, the nonce is important to keep private, because if you're able to get the nonce or at least part of the nonce from multiple different signatures, you can extract the entire private key. So, okay, so evaluation and results. So the authors, they ran 2 tests for proof of concept, and then they ran 2 tests to test the ability and the limitations of their attack. So first, they were able to prove that there is a correlation between the brightness of the LED and when the device is performing their encryption algorithms. So the first experiment they ran was with a security camera that they connected to via an API. And they used that security camera to like completely zoom into a card reader LED. From that, they were able to extract a 256-bit ECDSA key in just under 2 minutes. In their second test, that's the one on the slide over there, they used an iPhone to zoom into a speaker that was connected to a Samsung. So even though the speaker wasn't doing any encryption, you could see that the brightness of the speaker still somehow correlated to the Samsung performing encryption operations. And from that, they were able to recover a 378-bit key through that. And that did have some errors. That had 6 errors that they were able to catch and fix.
All right, so for future works, the first one we're gonna talk about is like basically just doing this on a bigger device like an ATM. So the thing with an ATM is it performs like multiple cryptographic like operations. So one has to like read your card, but 2, there's like a pin thing. Then there's also like networking that has to do. And basically, there's also a number of LEDs on the ATM. Obviously a card reader for one. So basically we can probably read these like fluctuations of light or the fluctuations of the LEDs to gain like sensitive information of the ATMs, which could be harmful, and that's kind of what the attacker wants. 2, another future work to consider is comparing LEDs. So all these LEDs basically are directly influenced by power consumption, and how they flicker can kind of how aggressively they flicker kind of can differ from one to one. So if we if we have there's certain LEDs have like different leakages, and like some may exhibit stronger or weaker. So as a defense mechanism, having one that like exhibits a weaker leakage is probably ideal. And then lastly, with electromagnetic interference, so a lot of these LEDs share like a power rail with microcontroller. And then this, if you send like an external electromagnetic field, what could happen is an attacker could, for example, amplify the LED. And then that could be basically detrimental toward to whoever owns the device and wants to secure it. So the three discussion questions I have today. One, what hardware modifications could be implemented to decouple the power LED's brightness from the device's power consumption, basically preventing this attack. Two, in what scenario, moreover, like what other devices could this attack be performed on? And three, considering the prerequisites of this attack, how feasible is the attack in a real world scenario? And then how could we also improve this attack's feasibility? So to start off with that first question, does anyone have a suggestion? Okay, so the most obvious suggestion I think is, well, first of all, these card readers, the LED that's on them is actually pointless because it's only to track their status. So you could just remove that for one, but if you really wanted to keep that LED, you could include one or more that kind of flash at random intervals. Therefore, none of that kind of happened. Therefore, like you can't really read the cryptographic operation, or you could just turn the lights on. It's a pretty simple solution, I think. And then two, so other devices you could do this to, so like a smart lock or like a network router is probably a great example. And then three, does anyone have like an idea of how to improve this attack's feasibility? All right, we're also short on time, so I'll just say, so the first one I kind of think of is, the biggest issue is kind of like the line of sight. You basically need to have the camera right next to the LED. The lens has to, the LED has to take the entire frame of the lens. But if you have multiple cameras, you could probably compromise this. So you don't need like one direct sight. You could direct line of sight. You could kind of have multiple that are like less direct. And that's pretty much all I have to say. That's it. We're good.
Thank you.
Next question.
I think the LEDs, you cannot remove them though. Oh,
Make a device that doesn't have it. It'd be like the tape over the LED, right?
Yeah, like, yeah, just like, I don't know.
well, I think people are attached to their LEDs. So. And they're always on. So I think the one thing that these guys did was they looked at the brightness change. So it's not like it's turning off and on. It's always on, just the brightness is changing, which is a little bit more tricky to defend. All right, who's the second group? Also, by the way, I think whatever I said at the first part, we were mute, so it hasn't been catch on the video. It's not impacted you guys, but whoever is watching it saw me 10 minutes
Do you need to join?
without any voice.
Yeah, you need to join with audio.
No, you don't need to join with audio.
Or just mute.
Yeah, you can also mute. Just make sure that your speakers.
Let me start.
Yeah.
Right, sure.
Hello, everyone. Can you hear me?
I'm sorry.
I'm Nat.
I'm Anirudh.
So the paper we're presenting today is Hands Come Back, a realistic audio electronic thread.
If you're speaking, you have to come here.
Okay, sorry. Okay. So the topic we are presenting today is Times Come Back, a realistic audio eavesdropping thread on a mixed signal SoCs. So okay, so first, what is timed attack? So from the traditional concept, the timed attack is like attackers taking advantages on unintentionally electromagnetic radiation from like electronic device to eavesdrop on sensitive information. For example, could be audio and video. So as showing on the right side, the pictures, like some people is using his laptop at the room, but the attackers from the outside of the room can steal the information by using the EM radiations. So, but right now with the technology improved, like the mixed signal system on chips, MSOCs has emerged. So the new EM leakages has like mainly like due to the like the switching regulator which integrated on the MSOCs.
So right now I'm talking about like what is MSOCs. On the right side, I'm showing like the architecture trend of the latest electronic device. So there are basically three tiers. For the first tier, like tier one, it's like separate chipset with different functions. For example, the digital, analog, and power circuits, they are in the different chipset. And for the tier two, they combine like the digital and analog together, but the power circuit is still being a single chipset. For the tier three, it's combining all these together, but the issue for that is like on the figure 4, is a cutting view of the like the tier three MSOCs. As we can see, due to the external system clock and also analog input or output, with the integrating switching regulators, the coupling current between all these threes within the tier three is much stronger compared to other tiers, which could cause the problem to the attackers could be much easier to get the EM radiations. So another concept here is called switching regulator. It's just a switch element that toggles between on and off at certain frequencies. So the thread model for this paper, it's like first it used the target device as showing on the right. It's a Bluetooth low energy MSOCs, and the target media is only audio information. But you assume like the attackers has no target device access and also it's in the invisible target environment, which means the carrier modulated audio signal like has lower attenuation compared to the real audio signal in the real environment. And also, its interference robustness is also high. The attackers can eavesdrop the sensitive information in real time by using the portable equipment.
So let's go through the experimental setup. Of course, the emissions from the MSOCs are weak, so the paper used a high directivity wideband antenna and a low noise amplifier combined with an SDR, which stands for software defined radio, in which the down conversion and digitization happens, and then all the data go through the laptop for the further pre-analysis and pre-processing and analysis. So they use two different signal sources. One of them is microphone, one of them is function generator to be able to create single tones. And of course, there are some noise considerations. So they turned off all the Bluetooth components in the environment, and also they did the experiment in the anechoic chamber. So at first they compared two kind of regulators. One of them is the switching, which is the target here, and one of them is LDO, which stands for low dropout regulator. So we can see here in terms of noise characteristic, there is some frequencies for the switching regulator that we can see some noise power here. Like the main one is 2 megahertz, and all the harmonics like here 4, 6, and there is a big power at the 8 megahertz. So in terms of noise, the switching regulator is not doing very well, but in terms of power consumption, we can see here the LDO is consuming as twice power as the switching regulator is consuming. So the switching regulator is more efficient than the LDO, but in terms of noise, it's not very good. So at first, they put the target in the distance of 50 centimeter by the antenna, and they use the microphone input, as you can see here. So if you take a look at this figure, and they sweep the frequency by a special criteria, you can see here, like at 192 megahertz, you can find a big unintentional signal to noise ratio, which is exactly the target of this attack. Here, if you compare these two figures for the LDO and switching regulator, we can see in these special frequencies, the switching regulator has a lot of power in the noise. So it means that the electromagnetic leakage in the switching regulator is too much, and it is vulnerable to this attack. They go further and increase the distance, like from 15 centimeter to 5 meter. As you can see here again, this is for different distances, increasing the distance. So we can see, even though there are some noises on the signal, but there are still some information in the signal. So actually, even in 5 meter, the switching regulator is vulnerable to the attack. Then they tried different kind of MSOCs, and only in one of them, which were for a Qualcomm company, there were no significant emissions. Probably they used some different shielding or materials, or design improvement. It means that there are some concerns in this company about this kind of attacks. So we can say that this threat is practical and switching regulator is a critical security risk.
Okay, so what Serena was talking about was done in like a chamber, but the researcher was actually doing it on the commercial devices. So they meet certain aspect of the target. So MSOC, where there's switching regulators, is integrated to the device, and they decided to pick out one Bluetooth voice recorder and 8 earbuds. And then the threat model for their commercial attack is they assume the target devices you cannot access them, so it's done wirelessly, and the attacker doesn't need to be in the same room, so it's invisible target environment, and then it can be done in real time, and those are the equipments that is needed for this attack. So you can see it's very lightweight and portable, so this can be fit in like a suitcase for the attack. And then the before the attack is done, they assume that the target model is known, so the earbuds is known. So they will use a probe and measure its frequency. Then during the attack, the antenna in the right corner there will pick up the EM signals at that pre-estimated frequency. And it will go through an SDR, LNA, so software-defined radio and low noise amplifier to do processing, and then that will enable the real-time eavesdropping on the model of the threat. So in the notebook there, so the there's information displayed on there, so that's the real-time conversation. The researcher also proposed a method to increase the range. So they essentially take all the signals and choose the strongest signal, and then align the phase of the smaller, smaller strength signals, and then combining them rather than doing a simple addition. And they found that that could increase the range a lot through this process. And then this is the result that they found. So the C1 here is the voice recorder, and then the second one is the earbuds. And they found that their proposed method has, and they can separate from noise easily. So this first channel here, like you can see, it's like blurry in the noise, and then this one is more significant. And then it's actually they can actually increase the range from 10 meters to 13 meters and 14 meters and still pick up the information. So it's done on all these devices, but two important findings that they have is the first one and the second one. So the voice recorder is significant because it can reach 13 meters. One reason is because it's a type 1 power regulator, which means it only has a switching regulator. So the switching action is a lot more, so the information is coupling in easily. And the second one is a type 2 device. So it's the same. All these are kind of type 2 as well. But this Xiaomi earbuds has like a wire across it. So it acts like an antenna that could radiate further. So yeah, that's the two important findings.
So the experimental setup that was taken into account for the purpose of the Tempest attack was we first start by assessing the feasibility of these of the audio signals via EM emissions, and as Nat and the other two mentioned earlier, we conduct these initial tests in an anechoic chamber to minimize EM interference. And the initial setup is designed to capture the audio signals which are leaked from these commercial devices like voice recorders, Bluetooth earbuds using EM radiation. And then these SOCs are tested both in the controlled environment and in a regular office setting, both to assess the risk of such attacks. Then the overall actual measurement of the signals is done using high directivity antennas. So these are set up to capture the radiated signals, and then we analyze the spectrum of these signals and understand the behavior in different settings. We also measure the maximum effective range of the attack, like where the audio signals are reconstructed from with enough clarity. And also the reconstruction of the signal based on signal processing techniques to improve phase alignment. And some of the methods that we use are adding additional filters to try to improve the clarity of the attack. And lastly, we then we validate the attack by trying to use realistic scenarios where the attacker can eavesdrop on the conversations that are available without any form of tampering. So the experimental setup, we captured them on 2 commercial devices in the paper. One is the Sogo voice recorder, the other one is the Xiaomi earbuds. These go up to a distance of about 10 meters in range. And the idea is to check if the audio signals can be captured across long distances. And the results essentially showed that the noise-based Tempest attack can extend the range and the robustness of these signals compared to other methods. Primarily, we take a look at a wideband, dense, and static characteristics of the noise emissions. And we use this method to leverage any extra addition of phase-aligned signals, which can enhance the ability to reconstruct the audio across larger distances. The feasibility of this is determined by not only whether it's theoretically possible, but also can it be done with off-the-shelf equipment. And to verify that, the paper uses multiple SoCs, and the analysis is used to check the vulnerability across different devices. The attack is then exploited across various audio signals which are coupled together with like system clock and SW-reg noises, which create EM emissions. And the analysis is done at various distances. So the audio information is eavesdropped from far distances than previously thought. And while obstacles can impact like the signal clarity, the paper is still able to see that effective eavesdropping is still feasible. And different devices show varying ranges of leakage and susceptibility to Tempest attacks. And the overall conclusion is that the critical security risks that are posed by these modern electronics, especially in IoT devices, is kind of underscored. So
I can jump in.
yeah, so some discussion questions. So one of the questions is, what are the different countermeasures which we take into account? This
Yeah.
ask them first, right? If
So we all use earbuds. What do you guys think? What would be a good countermeasures for this?
Why Apple
Yeah,
wasn't in that list.
Apple was not.
I think this paper was 2020 or I think before maybe.
Yeah, around that time.
It was
I
around that
forgot
time.
the
Probably it's even before the time, but anyway.
yeah.
Mhm.
But we looked at yeah, you can talk about this.
So some of the countermeasures that we look at are things like impedance matching. So the impact of signal coupling, capacitive coupling, the impact of high sensitivity often resulting in a low impedance, using metallic enclosures around critical components of the SoCs to block EM waves, line filters to signals and power lines that connect like the SoCs that can help in reducing radiation. As these guys talked earlier, LDO regulators are less power efficient in terms of consumption when we compare them to SW regs, but LDOs can, on the other hand, significantly reduce EM emissions. So, and then other techniques that we look at is, it's important to look at how the substrate package is designed with respect to like the substrate coupling, the positioning of the analog and the digital grounds, the interaction between these sensitive analog and digital components. And it's also important to look at how we can minimize noise spikes so we can have like a reduction in the amount of spurs. And the solution typically to that is using taking into account various switching parameters to avoid like noise patterns. So these are some of the countermeasures.
Yeah, so most of the countermeasures can be done in the design phase of the device. So all those and then I guess since we're out of time now, we just want to mention one last one, the scalable attack, because
Yeah.
Professor mentioned relay attacks last Monday, and I think we can use that technique to like increase further of the range of the attack. So yeah, that should be it. Thank you for listening.
Yeah, thank you.
All right, let's do one more and then we can have a quick break. Yeah, it's interesting. This particular paper was, all of these circuit techniques in order to make things more miniaturized, compacting more things into one device. In the past, it was like analog separate, digital separate, power separate. Now everything is in one SoC, which means that now the leakage is more integrated because now what you do in the analog domain is also leaked into the digital domain, which is exactly what's happening. And then before we get to do you know why we cannot just listen to the Bluetooth packets instead of like doing this? Well, like why not just picking up the Bluetooth packets directly and listen to that? Anyone want to say?
That's not encrypted.
They are encrypted, right? So basically what they do is after the encryption. So once the packets are decrypted and then you start actually looking at them, then these guys, its emanation is as at that point. So that's why you can actually leak this. All right, so let's talk about the third paper.
Do you want to control?
Hi, I'm Isha.
Hi, I'm Ankit, and our paper review is about FPGA-based remote power side channel attacks.
So the threat model is essentially that FPGA uses in data centers increases the risk of side channel attacks, both remote and physical. This is due to power monitor circuits that are built onto the FPGA, and they can be compromised such that another person or an attacker is able to view via power consumption. And the side channel attacks can affect either FPGA modules or other components of the system on a chip, such as like even a CPU. And in the image, you can see that there's a host and there's a few attackers that are also listening to the power consumption.
Awesome. So I just wanted to start with some background about what a power analysis side channel attack is, or a power analysis attack is. So essentially, kind of self-describing, it's just measuring the power consumption of a device or a module. So in this case, it would be like an RSA module on an FPGA. So essentially, the crux of this attack is that different operations, for example, like floating point operations versus integer operations, etc., have differing power consumption. There'll be voltage differences based on the different operations. So it's possible to kind of back out the exact operations based off the power consumption. Potentially, it's possible to back out the operations based on the power consumption profile. And I think what's key, I think the key development in this paper is that traditionally power analysis attacks always assume that you have, or the attacker rather, has physical access to the device, the potential victim device, or at least proximity to the system, to the victim system. Whereas this paper demonstrates that you don't actually have to have, physical access to the device or, complicated power analysis systems and devices to actually carry out this attack. And I just wanted to provide some just further power analysis attack background, more related to what this paper demonstrates. So, as I mentioned in the last slide, this paper demonstrates power analysis attack methods that don't actually require specialized equipment or proximity or physical access to the victim system or the victim device. And the way they do this is by utilizing a on FPGA power monitoring module, known as in this case, they particularly implement a ring oscillator circuit on the FPGA. So essentially a ring oscillator circuit is just a series of NOT gates, and you can measure power consumption that way. For this particular paper, if you see on your bottom right, they use a slightly more complex ring oscillator power monitoring setup, where they have a system of counters as well, so that way they can measure power multiple times and have a higher resolution result. And like we were mentioning, this on FPGA power monitor can be used for a power analysis attack on either other FPGA models itself, or on the broader system on chip, if the FPGA is in fact part of a broader system. And this, sorry about that. I just wanted to highlight this figure from the bottom left, which is taken from the paper as well. Essentially, it's just showcasing the kind of structure of the author's attack. So you see in this farthest most left image, the FPGA to FPGA attack, where you have the power monitor that's monitoring power from, for example, an RSA module that's on the FPGA. Or in this image over here, you see how this would kind of fit into a broader system on a chip, where you can still use a power monitor that's on the FPGA to, for example, carry out this power analysis attack that might, for example, be on a CPU rather than the FPGA itself. Awesome. So as kind of the last bit of background, I wanted to provide a bit of background on RSA accelerators. So, as we've learned, RSA decryption is expensive. And one possible avenue to kind of decrease the computational cost is to use what's known as a square and multiply approach, where the private key is decomposed into powers of 2, rather to kind of fit, the binary system that it's in. And this can reduce computation costs. Coming from a more signal processing background, I kind of liken it in some ways to how the fast Fourier transform also utilizes a base 2 system to speed up the calculation process. So yeah, and as we see, the top formula is the kind of standard decryption formulation. The middle formula, you can see this, the ciphertext that's then raised to the power of 2. That would be your square and multiply approach. And then finally, at the bottom is a figure that is taken from the paper, which is kind of the author's pseudocode for square and multiply RSA decryption. Awesome. And on this slide, kind of trending away from the background, we have the actual FPGA attack implementation and some key findings from the authors. So to start, just to kind of recap, we saw from the earlier slides that power consumption of the kind of square and multiply FPGA module, the RSA module that is, as measured by the power monitor, will differ depending on whether the private key exponent, which is this kind of exponential D over here, is either a 0-bit or a 1-bit. And in this particular setup that they did something called simple power analysis, or a simple power analysis attack, in which they simply looked at a power trace or a voltage trace, and then from there backed out what the actual bits in the private key were, or the private key exponent, rather. So you can see in this image from the left, which again is from the paper, you can see a sample key and its associated power trace. So as each bit in the key is being processed, this is the associating power from that module. And you can see, as the authors have noted, that there are differences, pretty stark differences between a 0-bit and a 1-bit in terms of like baseline voltage, for example, and offset. Additionally, kind of from the term RO or ring oscillator, kind of tying into frequency, there will also be frequency differences between when a 0-bit is processed and a 1-bit is processed. Awesome. So on this side, we have kind of the secondary scenario, which is not just, conducting this power analysis attack on the FPGA itself, but rather if the FPGA is part of a broader system on a chip, how one might be able to conduct a similar attack on a CPU RSA module, for example, if the RSA is implemented in software rather than on hardware. And the key reason that this could potentially be another vulnerability is that on a system on a chip, different modules, so for example, an FPGA and a CPU might share resources, primarily the power supply. So in the case that you are in fact sharing a power supply, the actual RSA decryption operations that are implemented in software on the CPU can still result in voltage drops on the FPGA power monitor. So essentially, for each bit that's being processed in the software-based RSA decryption module on the CPU, you might see associated power consumption variations on the FPGA monitor still. And this figure here, kind of analogous to the figure from the previous slide, showcases just that. You can see as each private key exponent bit is processed on the CPU RSA decryption module in software, how that actually affects the power monitor output from the still FPGA-based power monitoring module. So yeah. And finally, before we jump into some further analysis, just wanted to, in this slide, I just wanted to provide some of the a summary of the attack results. So essentially, the researchers decided to measure their power analysis attack performance in two ways. The first of which is that if you're given a single power monitor trace, so just one measurement, how many of the secret key bits were incorrectly identified. So essentially the bit error rate. And the second way in which they measured attack performance is how many total power traces it took to correctly identify the entirety of the secret key. And they essentially measured three different configurations of the power monitor. So the first is what they kind of initialize as PR, which is the scenario in which the attacker can define the placement and the routes rather, not routes, of the power monitor on the FPGA. So if they want, they can directly connect it to the RSA module, for example. The second one, what they term as ISO or isolated, essentially in this case, even though that power monitor module is still on the FPGA, it's physically isolated from the RSA monitor, or from the RSA detector, rather. And then finally is what they coin as a no constraints configuration, in which the power monitor can be placed anywhere on the FPGA. And without going too much into detail on the results table on your right, some of the key results essentially are that rather intuitively, the isolated power monitor, where again, there's no physical connection between the power monitor and the RSA decryption module, results in the lowest attack success, which makes sense. It has less access to the decryption module, so there's less information that can be gleaned from that power monitoring setup. And kind of conversely, and also intuitively, the attacker-defined monitor, again, where the attacker can choose where and how the power monitor is placed, results in the highest attack success rate.
So now we're going to go over a few different kinds of attacks and attack detections. So one defensive possibility is to have an attack detection with a power monitor. So because FPGA power monitoring can also be used to defensively detect attacks, it kind of plays on the theme that the best offense is a good defense. And one example is that when malicious users launch denial of service attacks by triggering like emergencies that might be not detected by traditional thermal sensors, power monitoring can help identify these anomalies. So a denial of service attack is just basically when the attacker keeps sending signals to the victim, making the victim unable to operate normally. Another kind of attack that is especially relevant for cloud computing is program identification. So I think as Ankit covered before, different program operations such as floating point or integer operations or cache misses and active computations, they have different power levels, and an attacker is able to kind of analyze these power levels or the power consumption levels, and then they're able to figure out which programs are running. And this is poses a really big issue for big companies that might rely on the cloud to store a lot of their data in, because they might be vulnerable to attacks, and this could reveal a lot of workload information or workflow, or process workflow that the company might want to keep private. So for countermeasures, the goal would be to make it more difficult for untrusted users to actually construct these power monitoring circuits on the FPGA. One way to do it is to insert random noise to hide the power signal. Of course, this has to be a trade-off because you don't want your SNR to be extremely low to the point where you're not able to actually extract the needed signal. You could also add dummy operations that kind of lead the attacker into the wrong direction. And the cons of this is that all of these countermeasures do come with some sort of overhead. Another thing you could do is have the actual technology to detect ring oscillators and have an FPGA provider check the design computationally. So using some level of code that detects is anything monitoring this power when it shouldn't be. So in conclusion, the integration of FPGAs does have a lot of security risks because attackers can exploit FPGA logic to conduct these powered side channel attacks remotely, because previously it was thought that these kind of side channel attacks would need to be done in proximity of the device, but now this kind of poses an entirely new threat level, especially to cloud or to shared environments. And because the power monitor can observe the consumption of programs on a CPU, it can also be used for attacks against a timing channel mitigation countermeasure. So some discussion questions we have are, one, how could cloud providers and data centers respond to mitigate the risk of these kind of power side channel attacks? So they could probably implement a strict resource isolation, making sure that multi-FPGA workloads don't share power domains. They could also use power management techniques, making it harder for attackers to actually extract meaningful side channel information. Could machine learning techniques be applied to detect FPGA-based side channel attacks in real time?
To attack or to defend?
I think either one. Sorry, I think this was supposed to say defend. Yeah. So they can actually be used, like stuff like neural networks can be used to classify attack patterns. And I think anomaly detection can be done by autoencoders. And the third discussion question is, how does the ability to conduct remote power side channel attacks change existing assumptions about security threats? So basically, the traditional assumption is that physical access is required for power analysis. And again, as we previously said, this just poses a lot of new risks in cloud environments, and it might be something that maybe the industry standard needs to be changed for, because it could be harmful for big companies who use the public cloud to store information. And if it's a particular company that, for example, everybody uses, like Amazon, and an attacker is able to get in, you could be, giving a lot of your information to somebody you don't want to give it to. And that's the end of our presentation. Does anybody have any questions?
Okay, speakers. Yeah, and then keep in mind that FPGA is becoming more and more available in cloud environments. There are lots of these instances. For example, AWS gives you an instance of an FPGA, so it's actually quite common that one can program an FPGA in a cloud environment. All right, let's have a quick break, and then we'll come back and then do the last two presentations.
Hello everyone. My presentation is synesthesia detecting the screen content via remote acoustic set channels. I'm Yaki and I'm the second year master student in ECE program. So I think everyone will encounter this scenario that when you're talking to professors or family members or friends, whoever, over voice over IP, these sometimes would appear as if they are not paying attention to the really interesting things you are seeing. So as this scenario, you are wondering what happened on the other end of the call. Are they actually listening to you doing some mathematics, or they're actually looking the X or other chatbots? So in this kind of scenario that you are getting the audio feed from their environment by playing as if you are on your speakers or microphones, but it's not really tell you what the screen content, and this is you are really interested in. So by the order that you are getting the feed is coming from the microphone that is pretty close to their screen. Can I use that? Actually, when the computer is rendering the visual content, it will emit the noise, and this kind of noise is really subtle and not mind by people. But what else if this kind of noise have the relationship with the visual content? It will cause a big problem. Why? Because people do a lot of things on their screens. They may surf on web, they may type in their credit card numbers, or they nature some weird obsessions that they do not want other people know. Actually, microphones are ubiquitous, and it is common for people to put their microphones nearby their screen, and also it is common for them to record. If you are in video chatting or the third party of the phones requires the permission to. Actually, sometimes the audio signal is available compared with the electromagnetic leakage, actually a visual content. So in order to figure out the leakage of the video content onto the audio signals, they draw the zebra. And what is a zebra? It's just white and black strips on the screen as we shown in the figure. And they also visualize the signals by using the spectrogram, and we can see the frequencies over time by this kind of spectrogram. We can see there is a predominant frequency at 4 kilohertz. So where is this kind of 4 kilohertz coming from? It could be coming from when the screen is rendering the visual content in raster pattern, and it refreshes at 60 times per second. Also, it correspondingly, it has 66 strips on the screen, so it maximizes rendering the 4K strips in the regular intervals at the same time per second. But this 4K and this 4K might be related, but they're not sure. So they localize where this kind of leakage coming from. They localize the screen power supply. And it conjectures that this kind of leakage coming from the different power draw of different devices while rendering in different intensity of pixels. But it's just a conjecture because they're not sure. And here is the lecture content. So what is this kind of the set channels? It always is acoustic or sound set channels. And what are the attackers' goals? They just want to extract secrets of the victims, like the website distinguishing or the password. And I guess it's a kind of template attack because they train on the similar model, and also the match or prediction the victim's real-time audio. And so next one is a contribution. As the attack scenarios I discussed before, it is possible for them to use webcam microphones or comedy microphones to video chat with. And so the second question is that the audio signal may be solely compressed and lost transmit to you. So the problem was that can you still see the same leakage at this kind of scenarios? And we can see it always the same spectrum we see visualized before. We can see the zebra frequencies using the webcam or comedy microphones, but it's over the Google Hangouts. And also we could say using the Alexa devices or the Google Home devices placed nearby the screen. But actually the smart speaker is transmitting and uploading your recording to the cloud, and we download them and we test it using the spectrum, and we still can see the frequency changes in the Zebra. Also, it is easier for them to place their phones directly nearby the screens. And they can also visualize and observing the leakage by using the parabolic mic in 10 meters far away from the screen. So what other attacker do? This is really important. First of all, they denoise the signal. There are two observations. The first observation is the amplitude modulation, because the pixel intensity modulation on the 62 kilohertz carrier in this example, and also the leveraging the redundancy to remove the jitter and drift. Actually, this is a kind of sophisticated chop signal method, but you can see the details in their paper, and they can get the clean signal. They use this clean signal to do some machine learning based attacks. They can do website distinguishing, the on-screen keyboard snooping, and also the text extraction. So next one is how did they do the website distinguishing? They actually displayed the various websites on the screen, and they detecting their traces. They located each traces by labeled the identity of the website that is displayed on the screen, and trained it into the neural network, because it's good for the time series of data. And also they do the keyboard snooping. Actually, it's an on-screen keyboard because the on-screen keyboard is safe against with the audio recording for some physical keyboard. It actually do not have the acoustic emissions of the mechanical keyboard have. And also when you using the on-screen keyboard, you press a key or you hover it, you can see the footprint because you're wondering which key you are pressing. And this kind of footprint will give you the traces. So the attacker using the same attack as a website distinguishing, and it's not defined which website they define the exact key. The next one is a text extraction. Actually, in this scenario, they cannot using the classifier before, because it's actually an open-end problem. Because people do not know the request of the output, and they train another classifier. They define the exact text in specific location, and they can use the same neural network to get the final output. And also they use the error correction within natural language redundancy. They assume that victim do not input any gibberish. They input the English or specifically words. The next one is a cross-screen train test. So as I said before, there's 3 motions attacker could do. So can we train on one screen and attack on another screen? Actually, it is true. But because of in this paper, the 4 screens are from the same model series, and they gave the very similar signals as the first right top signals, and also it could be even seeing the difference when using different attack models. So this is the result. I listed the different series of models of the screens they used, and we can see for website distinguishing is very high accuracy, and every test is above 90%. And for the
third one, parabolic microphone.
The third one is the parabolic microphone 10 meters, yeah. And for the keyboard snooping, they test horizontally and vertically displayed, and it's also high in accuracy. And for the text extraction, they can achieve up to 98% per character accuracy, and they could also extract or detect the probability higher than half for error correction. But there are some limitations, like they use a large space font or the no layout. So
Which application did you open the text? Is it like a notepad or a Microsoft Word? Where did they like type?
I think it's just on Ubuntu text pad.
Oh, okay.
Yeah.
Okay.
And here is the result for the learning from the multiple screens. The challenge is they found some overfitting for the neural network training. So the idea is they train multiple screens. And there is a trend that they train more screens, they will get higher accuracy, and it's up to 94% accuracy they can get, distinguishing between 25 websites and training up to the 10 screens. So there are some limitations. The first limitation is attacker prior knowledge. As I said before, that attacker knows the keyboard layout, the front, and the specific the key locations. So if they do not have those kind of prior knowledge, it will reduce accuracy. And also due to the acoustic transmission limits, it will limited in granularity strength. Also, it will have limitations in sampling rate because our modern devices are always sampling in 96 kilohertz, and this paper was using the sampling rate in 64 kilohertz. But it makes sense because this paper was published in 2019, I guess. So also there are some future work as limitations before. The first one is we could use the complex screen scenarios. Also, we could do the cross-screen generalization, or we may increase the fronts or layouts to test the different kind of screens. Also, we could do some robustness to diverse environments because it's in lab scenario, but we do not sure if it will work in our classroom or office somewhere. So there is some discussion problem. The first one is in this paper, we tested the accidental leakage of the screen content. So if we could get a high resolution or dynamic scenarios, if we combined with the electromagnetic emissions, thermal emissions, or kind of ambient reflections. And the third discussion question is about the biobehavioral and physical leakage. For example, if we give the differences in strength of the keystrokes and we violation patterns of the screen touches, could I identify the different users? Actually, is very important. And the third one is the side channel ethics. Actually, is there any harmless side channels existing while preventing the misuses? I think everyone can think about it, and that's all. Thanks so much.
Another question? Yeah.
I have a question. What kind of screens were these? These like LCDs?
Oh yeah, it's LCDs and yeah, it's LCDs.
Well, I think there was a table listing them like.
Yeah, the table is.
Dell and Apple.
Yeah, I know they're like OLED or
I
like
think-
LCD, or I don't know like how new or old they were. I don't know, it's the technology.
Oh, I see. I think monitors are all else. Well,
Like all of them are OLED now.
yeah, well, yeah, this is 2020, so. Any other questions? Great job.
Thank you.
Very last group. Yeah, this is very kind of crazy, kind of 007 kind of attack. That there is a microphone, that you have a monitor, and you kind of like, watching things, and then it's sending things over a microphone, which is interesting.
Recording in progress.
I think it's frozen.
Yeah.
Oh.
Maybe I can try it again.
It's fine.
Or you have to share theirs, do the screen.
Oh.
Your parents' screen.
Right?
Yeah, okay, so I'm Dao Xian, this is Fan. Today we're presenting a paper called
can one hear the shape of a neural network snooping the GPU via magnetic side channels? So traditionally, you would expect a neural network's architecture to be IP, so you don't want like you don't want it to be publicly known. So the problem here is that is whether you can reverse engineer a neural network's architecture while it's inferencing on the GPU. And apparently the answer is yes, but under certain assumptions. So jumping straight into the assumptions that this paper made, one of it was that this whole paper is an EM side channel. And so you would have, your assumption would be that you would have physical access to the GPU's power card. And what you would do is you would put your antenna right on top of the power card and record the EM leakage from the power card. So it is more similar, it is technically a power side channel kind of work, but the antenna, the justification for using the antenna that way is that it is non-invasive. The other assumption that you want to make is that your adversary can perform inferencing on the GPU. So you can imagine this as sort of like a cloud or a infrastructure as a service kind of situation here. And the important thing to note here is that your adversary needs to know the input size, and it needs to be able to choose the batch size that the GPU is processing at runtime. So the high level attack description is that once you get your EM trace, the way you would process it is you would just use another neural network to process that. So the full methodology from the adversary's perspective is that you would first need to assemble a data set containing like EM traces from your own GPU. Then you would train two different neural networks, one for what they call topological recovery. So what you get is stuff like how many layers the network has, what kind of layers each of those stuff are. And the other one the other network you would train up is the hyperparameter extraction. So you get stuff like layer size and the activation function of each layer. Then after you get your models ready, you would run your GPU inferencing to get your EM trace. And I guess the most important thing to note for now is that you need to choose a large enough batch size, because if your batch size isn't large enough, you have some noise from the GPU, and you wouldn't get a high enough SNR. And this is important to note later on, but for now we can keep it this way. And then what you do is that once you get the EM trace, you pass it to these two neural networks that will give you your details of your of the victim's model. So yeah, I'll pass on to Fan to talk more about those.
Batch size, you mean like continuous inference?
No, like so at once, how many, because it's a GPU, you can create like multiple inferences
so
on
you
it.
do multiple
So multiple of
inferences.
it, so that you have multiple walks running at once.
Okay.
Yeah.
And there are two information the author want to steal. The first part is the topology part, and another part is the hyperparameter part. For the topology recovery, the author will first capture the magnitude signals from the power supply using a sensor here. After they obtain such information, they will use these things to train a bidirectional long-term memory models. And after the train these models, they will apply this to classify these different signals to the different layers here. We can see from the figures right there, the different signals were represented to different layers. Part of them are very easily recognized. For example, the convolution layer here, you can see it's higher than most of the other layers. But for part of the layer, for example, the second one and the third one, they look very similar. So this part may be harder to for the modules to recognize. For the hyperparameter estimation part, they will also use some pre-trained DNA models to identification these things. And for each pair of information, like each layer type and hyperparameter type, they will train one DNA modules. So for all kinds of, different layer types and hyperparameters, there are a bunch of different DNA modules they need to train. After they obtain the output of the DNA modules, the problem here is that there will be consistency constraints of the modules of the DNA modules. For example, the output size of one layers must the same as the input size of the next layers. And there are also other constraints similar like this. So, but the output of each DNA module will be independent. So how to combine this together to all of these constraints? They formulated the whole problem as an integer programming problems, and they will use some servers like IBM CPLX to solve these problems here.
so that you can formulate the whole hyperparameters and layer size as a together, so they can be consistent in the whole as a whole. Here comes to the evaluation part. Actually, the methodology they use is around a bunch of settings. Like they have evaluated on 6 different GPUs, and the sense of placement is the same as stretch model I mentioned before. Like they just directly put it into the power near the power. And because they need to train the DNA modules, it's very important for them to choose a training data set and the test data set. Actually, they randomly generated 500, networks, and they use different, varying depths here. Yeah, there are over 70,000, total layers used in the training data set. And all of these were also including some well-known structures like WGG and ResNet. And for the input images they use, actually they are also, a bunch of choice like ImageNet or the size of ImageNet or size of SEPA10. And for test data sets, they use a fully separate from separate data, and they choose 64 random networks for testing here. Here is the results of the accuracy of the layer part. We can see that the classification accuracy of the layers is quite high among all of these layers, especially in something like convolution layers or STM layers. It's over 99% accuracy here. But for part of the layers, like the average pool, which is here, you can see this is relatively low. I think that's mainly because, as we have shown in the previous figures, that part of them are hard to distinguish, but part of them are really easy to recognize, even by human. And for the hyperparameter estimation, here is the result of over 1,000 convolutional layers. We can see that for convolutional layers, the 5 different hyperparameters, the accuracies, all of them are very high here. They are all higher than 96%. But actually, in this paper, they also do not mention, other layers results like the Béchamel layers or other layers. They only mention the convolution layers here. So there's another problem is that, as we have mentioned before, there are constraints. There are constraints on the model layers and hyperparameters as a whole. So how can we evaluate the constraints we have mentioned before? What the paper do is like they test it using the transfer attack. They will build a surrogate model using the topologies and have parameters they steal from the victim model here. And then after they obtain the model structures and architectures here, they will train this model on a SEPA10 dataset to obtain the surrogate model. And they will use these surrogate models to generate some adversarial samples by adding some, random noise or things like that. And they will apply these adversarial samples to these victim models to test whether they also, outputs, wrong on these, adversarial samples. If they are success, which means the structure and weights of the surrogate model is quite similar with the victim models here. So by doing this transfer attack, they can test the layers and hyperparameters as a whole to test whether both of them works well in this surrogate models. The results show that most of these target models works very well, except the XNet here. We can see that the successful rate of this one is quite low for all the other models here. And the first 4 line means that they test all of these modules in different GPUs here, and the last 6 one is the surrogate models here. They want to,
Okay, so one of the interesting results with respect to hardware was whether it was testing the accuracy across different GPUs. So the question we want to ask is whether how important is knowing the specific GPU or brand that the victim is using. So the previous results that you saw, most of those data sets was built under the assumption that you know the exact GPU, so you can construct your data set based on that specific GPU. But if you don't know the exact version, you need a generalized data set containing multiple GPUs and then each of their own labels. So there are two kind of cases they evaluated. The first one is if the GPU, the victim's GPU is in the training set. The other one is if it's not. So this result kind of demonstrates it. So the top row shows the results that are not in the training set. The bottom row shows that when they are. So the bottom is kind of expected. You get high, relatively well performance results. But for if your GPU is not in the training set, what they noticed that more recent GPUs you get a high accuracy. And the conclusion they came up with was that you don't need to know the specific GPU on it as long as the data set has similar kind of GPUs. So like, for example, you can see at the end there, you have like 3 1080 series, and those kind of get better results in a way, as opposed to like the 960 series. Yeah. So on to prevention, there are 3 kind of suggestions they gave for like preventing this kind of attacks. The first one was that recall that you need to have like large amount of batch sizes to have a high enough signal to noise ratio. So one of the ways you can prevent this, you can limit, the cloud provider can sort of like limit the amount of batch size that's being processed by the GPU, but you know, at a performance cost. The other one was to prevent the adversary from having a proper training data. So you could have like a non-standard framework for inferencing, but they also said that it's going to be difficult for that. So the last solution that they provided was that for reconstruction, was that because when you want to reconstruct, you need to identify different GPU operations. What you can do is you can essentially add in additional like dumb operations. So like the top one is like the proper one. At the bottom one, you can see like sort of like red signals that are like dummy operations that don't do anything to the results, but they sort of like model the EM trace that you get. Now, if you can't do any of those preventions, what they do suggest is jamming. So the idea is that you run background processes on the GPU while the GPU is inferencing. And so as the you can see as the background utilization increases, the accuracy that you get drops steeply. Yeah. So I guess on to discussion and future works, we have 2 sort of like questions that we thought were interesting. The first one was whether you can extract weights of GPU using EM. And the other one is whether the same attack could be extended to like, say, more complicated models like GANs or transformers, given that this paper was published in 2022. It's a relatively old paper. Yeah.
Thoughts? Yeah. I was kind of wondering, did they test the withholding the GPUs on any of the more modern GPUs? Because I noticed they were like pretty old models.
Yeah, so I don't those were the kind of like models like GPUs that they tested out. Just 1080 is the most recent.
1080? So like how old is 1080?
I don't know, man. It's like 50 series now.
Oh yeah, right. Like, not too bad. I don't think it's gonna be fundamentally different, the newer one. Like what has changed? Like nothing has changed.
I think the more interesting thing to note is that if we're talking about GPU series, most cloud providers, they give you like A100s, D100s. You normally wouldn't be able to buy those without like forking out large amounts of money. So if you want to reconstruct different data set, it might be difficult as well.
It might be difficult. Yeah.
But yeah,
Probably one of the reasons that these guys go with like older ones.
Yeah.
They don't want to buy the like the brand new ones.
So
Any other questions or thoughts? What do you think will happen with transformers? Anyone wants to predict?
My guess would be that, well, I think the reason that my guess would be that the CNN and the LSTM are easy to detect because they're like lots of repeated operations, right? So presumably attention should also be easy to detect because it's a lot of repeated operations like that.
okay. So with regards to leaking for weights, there is a upcoming paper in Nutanix 2025. It's called Barracuda. So GPUs do leak DNN weights. It's also an EM side channel, but instead of putting your antenna on the power cord, you have to put it on the chip to get a high enough granularity on your EM trace. So one of the interesting things was that they assume that your adversary knows the architecture, which is building on top of this work. And then they use more traditional side channels methods, so like differential analysis, and like they treat that as more of a cryptographic kind of operation than an actual AI inferencing kind of a problem. Yeah, so that's for leaking weights via
EM. Now, with regards to whether or not it's possible, in theory, it might be possible to train some neural network to sort of extract the model. So you can, I guess you can sort of like in a way extract it, but on the other hand, what I've noticed is that there's not much work in using EM to extract more complicated architectures. So I guess that's something interesting to work on. Yeah, that's it.
Complexity is better for these because they're more different. Like the ReLU was the hardest one for them. Convolution was like very easy. So I'm assuming that transformers even would be better. Weights might be more different. All right, perfect. Any final questions? Don't forget to submit your reviews. As I said, I think the first 10 minutes of my presentation was muted. So I'll probably just record it then another time and share it with everyone. And there is also this. Ooh. Anyone wants? It's not yours. Who was like someone left? Okay. Anyway, all right. So and then don't forget about your projects. Go into the Google Calendar and make an appointment. In the appointment, you just need to describe what you're gonna do. And I'm gonna just check off your name. One person per group is enough. You don't need everyone to show up. And video assignment 2 is also out, so do that as well. And then we're gonna continue talking about things next week. We're gonna start talking about digital attacks. Yep.